Hello students. So I hope you all have understood from my previous video session how singular value decomposition can be performed for a 2 cross 2 matrix. Now this video session is going to be on another matrix where we will be finding out singular value decomposition. To be specific, it is an M cross N matrix. The procedure remains the same except for finding the value of U3. So let's start. The matrix is given to you 1 1 0 1 minus 1 1, and on this particular matrix you have to find singular value decomposition. So as we all know, can be split into three major components or elements: U, summation and V transpose. Where U and V, they are basically the unitary matrix which are orthogonal, and summation is the diagonal matrix. So here, because we have got three rows, we are going to consider three values of U. So U is equal to U1, U2 and U3. So as we all saw in the previous lecture or session, U1 is nothing but 1 upon singular value 1, that is sigma 1, A into your V1, where V1 is the eigenvector. U2 is 1 upon sigma 2 into A into V2. Now you all must be wondering that in a similar manner we can find it for U3 also. But this is not a 2 cross 2 or a 3 cross 3 matrix. This is an M cross N matrix where M represents the number of rows. So it is 3, and N represents the number of columns, that is 2. So it is a 3 cross 2 matrix. So the procedure followed to calculate the value of U is slightly different. So let's have a look. Summation calculation remains the same, that is singular value 1, 2, here there should be 3 also. So this should be singular value 1, 2 and 3 multiplied with I, where I is the identity matrix and it will be a 3 cross 3 matrix. And here V also, it will be V1, V2, and let us see how V3 can be obtained. So the first step for determining singular value decomposition is A transpose A. So the matrix is given to us, we carry out its transpose and multiply it with A, and on performing matrix multiplication you get 2 0 0 3. Now we have to find out the eigenvalues and eigenvectors. So A transpose A is treated as S. You will subtract it with the identity matrix. Here we are first treating the 2 cross 2 dimensions, and then we will see for the 3 cross 3 dimension. Alright, because you all must be wondering over here why we have not taken 3 cross 3 identity matrix. The reason here, when we perform matrix multiplication, we got a 2 cross 2 matrix. So we will be multiplying it with a 2 cross 2 identity matrix. On determining or carrying out the determinant of this particular matrix, we will be getting two values of lambda, where lambda 1 is 3 and lambda 2 is 3. So the higher value will be kept as lambda 1 and second highest value will be taken as lambda 2. In descending order, we will place the values of eigenvalues. Now, as we all know, singular value is nothing but square root of your lambda 1. So that is going to be square root of your 3. And singular value 2, that is sigma 2, is going to be square root of your 2. Now for these two, eigenvalues, we have to find out the eigenvectors. So instead of lambda, we will substitute the value of lambda 1, which is 3, and a11 and a12 are the new vectors that we have considered, and we get two equations. By orthogonal transformation, a11 square plus a12 square is equal to 1. So in that case, when we consider one of these equations, and in that case we substitute the value of a11, which is equal to 0, in this particular equation we get a12. So a11 is 0, a12 is equal to 1 when I am considering lambda 1 equal to 3. For lambda 2, the same procedure is followed, where instead of 3, now we will substitute the value of lambda to be 2. The same procedure is done, orthogonal transformation is performed, we get the value of a11 to be 1 and a12 to be 0. Now we can find out the eigenvectors in this case. So when lambda 1 is equal to your 3, we have got a11 and a12, which is 0 and 1, which is v1, the eigenvector. When lambda 2 is equal to 2, that time we have got a11 to be 1 and a12 to be 0, which is v2. Now, as we all know, we have to find out the values of u, summation and v to calculate or obtain the singular value. So now u is nothing but u1, u2 and u3. So u1 is 1 upon singular value 1 into a into v1. Singular value 1 is nothing but square root of lambda 1. So 1 divided by square root of 3. A, which is given in the question, v1, which we have obtained over here, the eigenvector. On performing matrix multiplication, we get the final value of u1 to be 1 upon root 3, 1 upon root 3, 1 upon root 3. In a similar manner, we will be finding out for u2. So 1 upon root 2, then a, and here it is 1, 0, the value of v2. So on performing matrix multiplication, the value of u2 we get is 1 divided by root 2, 0 minus 1 divided by root 2. Now, the most important part to calculate SVD for an m cross n matrix is to find u3. So we cannot apply the regular method as we have found out for u1 and u2. So the procedure is to apply Gram-Schmidt process. Now what is this process is, to find out the value of u3, we need to consider the transpose of u1 and u2. So this is the value of u1 and this is the value of u2. So we take the transpose of this. And now what do we do is, to just obtain uniform values, we multiply the first row with root 3. So we get 1, 1, 1. And we multiply the second row throughout by root 2. So we get 1, 0, minus 1. Now this matrix is called an augmented matrix and it is set to 0. I'll tell you what does it mean. That is, we need to find the null space between the two vectors u1 and u2 transpose. Alright, so basically we are just going to write these values here and we will augment it. You can either use dots or you can use a straight line and set it to 0. Alright, now what we are going to do is, we are going to perform your reduced row echelon form. This is already done in matrices in your lower standards, but still I'll emphasize on this part. So we will perform reduced row echelon form. Now what is the procedure of reduced row echelon form is, if you see over here, I have drawn a ladder. Okay, so this ladder is nothing but the first element in your first row should be equal to 1. Your second element in the second row should be equal to 1. Third element in the third row should be equal to 1, so on and so forth. So that element is called as pivot. So this 1 is the pivot for the first row. For the second row, when I get 1 over here, that will be called as the pivot. Another condition is all the values below the pivot should be equal to 0. Now here, because there are only 2 rows, there is this only one condition, that it has to be 0. So what is done in this case is, to obtain this particular 0 over here, we need to get this 0 because we are following the ladder. So simply we perform row transformation. So R2 minus R1. So 1 minus 1 is 0. 0 minus 1 is minus 1. Minus 1 minus 1 is minus 2. 0 minus 0 is 0. So this is the pivot. Below the pivot the value is 0. So the condition gets satisfied. Now we jump to the second pivot. Now here this has to be basically plus 1. So we multiply this particular row R2 by minus 1 throughout. So this becomes plus 1. Alright. Now what is the condition over here is, we need to have the values above the pivot also 0. Below the pivot and above the pivot the value should be 0. So simply we will do R1 minus R2. So what happens is, 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 2 is minus 1 and 0. So now we have obtained two pivots. The value below the pivot is also 0. The value above the pivot is also 0. So what happens in that case is, this particular value what is remaining is your orthogonal vector. So minus 1 and 2. Now simply what we do is, we multiply this vector by minus 1. This is a standard procedure. So we get 1 minus 2. And because we have got 3 rows, so we add 1 at the bottom, so that it is in line with U1 and U2. So we have got 1 minus 2 and 1. So this gives us U3. But we have to make this U3 orthonormal, which is nothing but U3 cap. So what is done in that case is, we take the square root and we take the square of these values. So 1 square plus minus 2 square plus 1 square. The square root is nothing but square root of 6. So U3 is 1 upon square root of 6, 1 minus 2 and 1. So we multiply this root 6 inside. So now U3 cap is your actual U3, which will be with your U1 and U2. So this is the U1 value, U2 value, and this is the U3 value. So we have obtained the value of U. Now summation is singular value 1 comma singular value 2 multiplied with I. So because we have considered U1, U2 to be 2 cross 2, so in that case we have got your sigma 1, 0, 0, sigma 2. And this is nothing but I. But students, if you see, we had got 3 rows and 2 columns in A. So in the singular value, in the value of I also will include 3 rows and 2 columns. So if you see, this is not a complete identity matrix. So it is 1, 0, the third column is missing. So 1, 0, 0, 1, 0, 0. So if you see diagonally, if we place 1, 1, then it is a 3 cross 3 identity matrix. But because the value of A is 3 cross 2, identity matrix values also will be taken as 3 cross 2. We know sigma 1 and sigma 2 values, which is nothing but square root of lambda 1 and lambda 2. We will perform matrix multiplication of these two matrices and get the summation value. Now finally, we know the eigenvectors. This is obtained from the value of V, that is V1 and V2 over here. Alright, so 0, 1 and 1, 0. So here we need to get the transpose. So this is V. The transpose also remains the same. So now we have got U, we have got summation, we have got V transpose. On performing matrix multiplication, we get the same matrix as A. Singular value decomposition is performed. If this value matches with the value of A, it indicates that you have correctly performed singular value decomposition. The matrix multiplication can be done through a calculator. I hope you have understood how singular value decomposition can be performed for an M cross N matrix. Thank you.